Okay, so good afternoon. Let's get started. Last class, we were deriving the equation for the on current of a transistor, right? And we said that the on current we can show for an NMOS transistor is IDS is equal to mu n C ox W by L into, I'll bring the VDS out, VGS minus VT minus VDS by 2. This is when? What is the condition on VDS? So this is VDS is less than or equal to VGS minus VT, right? And what happens after that? The current just saturates, right? And you get half mu n C ox W by L into VGS minus VT the whole square. Okay, this is VDS greater than VGS minus VT. And this we discussed was because VGS minus VT minus V should be greater than 0 at all points in the channel. So the worst thing is at the drain end. And therefore, if you apply that condition, you will find that VDS has to be greater than VGS minus VT for it to be, for a current to increase, right? So after that, it just saturates. And what happens? There's one more condition. What happens if VGS is less than VT? The model is basically the current is 0. Okay, let me put approximately 0. It's negligible actually. Okay. So now let's just complete. So this is what we call a long channel transistor, which means that the drain and the source are sufficiently far apart that we really don't have to worry about second order effects. Okay, next we will derive a short channel transistor's drain current by incorporating various second order effects. Okay, but before that, let me deal with what is known as the body effect. Okay, so what was the expression for the threshold voltage? We said it is psi s plus what? 1 by C ox root of 2 epsilon Si q Na into mod psi s. Okay, why the mod psi s? Because for an NMOS transistor, the surface potential is considered to be positive. That's the convention. For a PMOS transistor, the surface potential will be negative. Okay, because we have to apply a negative potential on the gate, and therefore the surface potential will also be negative, and therefore inside the square root you have to put a modulus. Okay, but for a NMOS transistor, it's basically just square root of psi s. That's all, because psi s itself is supposed to be positive, right? I hope I got this expression right without missing any other term for the threshold voltage. Yes, 2QNA. Okay, so what was the structure like? We said we had a P substrate, then we had our gate with a metal and then the oxide, then we had some depletion like this. This was N plus and P. Then we applied a gate potential. This source we assumed was grounded, that was our reference terminal. This is the drain, and this contact is basically the body. Okay, and we assume that the body was also grounded earlier. Basically the body was at the same potential as that of the source. But of course this is a fourth terminal and there is no need to tie it to the source always. You can always apply a different potential on that body terminal. Okay, so what happens when you do that, right? So let's now assume that our VGS is some positive voltage. So what happens is you have some negative immobile charges that have been created here. Okay, and then you can have some free electrons typically if the body was grounded. Okay, then all the work that is done to invert the channel is done by the gate. Okay, and that was the definition of threshold voltage. Now if I apply a positive potential, let me say that VBS is greater than 0. I am going to apply some positive potential on the VBS on my body. Okay, so again the theory behind this body effect is very complicated. So for the purpose of this course we are going to abstract it out, and we will treat this body terminal like a back gate. Okay, so there is a depletion region, okay, which is basically like there are no free electrons, you just have an electric field from some positive to negative charges, right. So what we are going to do is, if I apply a body potential VBS which is greater than 0, then this capacitor here, right, this capacitor here is going to act like a back gate capacitor, just like the silicon dioxide on top provided control for the gate. This capacitor behind here is providing some control to the gate, to the channel, right, and that can be controlled by the body terminal. So just like we said, if gate potential goes positive, you start getting some negative charges at the channel. Similar thing will happen here. Okay, this is again only an abstraction, it's not a physical picture that we are talking about. Okay, so you can treat this like a back gate, and therefore if VBS is greater than 0, I will already get some negative charges. Okay, so now what should happen to the threshold voltage of this transistor? It should decrease, because the threshold voltage is defined as the work done by the, not work in joules, it's the work done by the gate potential in order to invert the channel, which means I have to get a negative free electron concentration at the surface, which is as much as the whole concentration in the bulk. But now if the back gate has already provided some electrons or has already depleted the channel partially, then the gate needs to do lesser work in order to invert the channel, and therefore the threshold voltage VTH should come down. Okay. So therefore I will now modify this threshold voltage term to include this body effect as well. Okay, and it's not possible, by the way, to derive this from scratch or first principles. We are going to I'm just going to write an empirical equation. Okay, I'll tell you what the empirical equation means. VTH is basically VTH naught. Okay, I'll tell you what VTH naught is, plus some term into root of mod of psi s plus VSB. Okay, note that I am reversing the term, it's not VBS, now I am saying VSB, minus root of mod psi s. So what is VTH naught? It's the threshold voltage at VBS or VSB equal to 0, which is the earlier expression that we had derived. Okay. So now let's just go through the same analysis that we did. If VBS has to go up, what should happen to VSB? It should go down. So now therefore the threshold voltage should, what should happen? Which direction should it go? VBS greater than 0, we said threshold voltage should decrease. So when VSB decreases, you want the threshold voltage to decrease. Therefore it's basically just, so what is the sign of this gamma? Positive, right? VSB decreases, you want threshold voltage to decrease as well, right? So this gamma is an empirical body effect coefficient, which means that there is no physical interpretation to this term very accurately, right? What you do is you construct a device, make measurements in the fab by applying different body potentials on the transistor, measure the threshold voltage by some technique, right? And then you fit this data to this gamma. That's what you mean by an empirical parameter, right? So this whole device physics modeling equations that we will be talking about are semi-physical or semi-empirical. You cannot derive everything physically and get a simple equation to deal with, okay? So what we are doing is known as a compact model, which means that whenever it becomes very complicated or difficult to model something, you resort to an empirical model. So that parameter you will just fit, which means that if I just scale, for example, if I take the previous equation, right? If I scale oxide thickness Tox, if I take this equation here, if I scale Tox, then I can guarantee that the threshold voltage will vary as per this equation. Now here when I do this empirical fitting, if I change some parameter, there is no guarantee that it will work. It is very, very specific to what it has been fit to. So you make measurements on the transistor for certain lengths, certain widths and all that, and then you can guarantee that this is the best fit for these particular parameters. But if you change it arbitrarily and apply a very large width or a very small width, then there is no guarantee that the model will work. This is the flip side of an empirical model. It simplifies the equation but does not guarantee scalability into all regimes of operation, okay? So yeah, so gamma is body effect coefficient and it is greater than 0 for NMOS, okay? What's the dimension of gamma? What's the dimension of VTH? VTH is volts, VTH naught is also volts, okay? So this is, by the way, in volts. So therefore gamma has to be in root of volts, okay? So with that what we have derived is the threshold voltage equation and the on current equation for different regimes, linear, saturation and all that, for a long channel transistor, okay? So before we proceed to the short channel transistor, let me quickly look at what will the ID VGS look like. I am going to look at ID versus VDS for different VGS values, okay? So I will write the equation here. ID is mu n Cox W by L into VDS into VGS minus VT minus VDS by 2, and this is for VDS less than or equal to VGS minus VT, and after that it's mu n Cox W by, I'll just say 2L into VGS minus VT the whole squared for VDS greater than VGS minus VT, okay? So I am going to now assume that all my VGS values that I consider in this plot are greater than the threshold voltage, because before that the current will just be 0. So I am not interested in that. What will the curve look like as I look at various VGS values, okay? So let us consider some VGS 1, 2 and 3, okay, where VGS 1 is less than 2, less than 3 different potentials. So what will the curve look like initially when VDS just exceeds 0 or just exceeds 0? In what region of operation will the transistor be? Yeah, it will be in the linear region because VDS is less than VGS minus VT. So this will basically be a quadratic thing. Till what point will it go? Yeah. So this is VGS1 minus VT. This is a quadratic line, and what happens after that? It just remains like this. So this is VGS1. Now I increase my VGS to a higher potential. Of course, both are beyond VT. So what will happen? It will again start. Okay, now the question is, will the current be like this or like this? What will happen? It has to be greater than, because if you fix a particular VDS, higher VGS means higher current, right? Therefore, it cannot be this particular term. Now I take it till here. Now let me extend this line. So will this come and saturate here? Why? Yeah, so it will proceed to be in the linear region until VDS has hit VGS minus VT, and now my VGS has increased. So this will go further up, right, and then saturate somewhere here, VGS 2, correct? Now I consider the third VGS, right? Similar thing will happen. I am going to start, obviously the current will be much higher. Okay, by the way, let me draw this line here. This is VGS2 minus VT. It will start much higher, and somewhere here it will saturate. VGS3. So this guy is this is VGS3 minus VT, and this was VGS2 minus VT. Now the point to note is that if I fix a particular VDS, right, in the saturation region where all three transistors are now in saturation, right? So let me consider this particular point here. What should be the relation of the currents ID1, ID2 and ID3? Let's say this guy is ID1, ID2 and this is ID3. So what should be the functional relationship with respect to VGS here? It should be a quadratic relationship, right? So if I increase VGS little bit, then the saturation current goes up as square of VGS minus VT, right? So therefore this spacing will now be quadratic. Okay? Clear? Any questions here? Because next you will see that when we go to a short channel transistor, this quadratic relationship will vanish and it will become a linear relationship. So if you want to find out if a transistor is long channel or short channel, this is one of the things that you can look for, whether this thing goes quadratically or linearly. Okay? Now how does IDS versus VGS look like for various VDS values? And before I even proceed here, let me say this is linear and this is saturation. Now this is linear and this is saturation. This is linear and this is saturation. Okay, in that plot. So now I want to look at ID versus VGS. For various VDS 1, 2 and 3. Similarly, like last time, VDS 1 is less than VDS 2 is less than VDS 3. So what will happen to the current if VGS just goes slightly above 0? Some small value, let's say 1 microvolt. VGS goes to 1 microvolt. Yeah? Has to be 0, right? Assuming that the threshold voltage is about a couple of hundred millivolts, hundreds of millivolts, obviously the current is going to be 0. Therefore, this will be 0, right? Now at some point this will take off. What is that point? The threshold voltage, right? And then as soon as my VGS exceeds the threshold voltage, if VDS is now fixed, in what region of operation will the transistor start? Huh? How does it matter? Let's say my VDS, let's say I have taken it to be some 100 millivolt, some small value. VGS just exceeds the threshold voltage. It has to be saturation. So unlike the ID versus VDS plot where the transistor starts in linear and then goes to saturation, ID versus VGS will start in saturation and then go to linear, right? So therefore this is now going to be a what kind of curve? Quadratic curve, right? So you will have a quadratic curve until what point? Right, there is some point where this thing is going to change, this behavior will change. Huh? So when will the region of operation change? It is starting in this region. VDS is greater than VGS minus VT. Now I am sweeping VGS. At some point VGS will reach a point where the transistor goes into linear region. So what VGS is that? VDS, exactly. So this is VDS1 plus VT. After that, this has to be it's a linear thing. Look at this equation. As a function of VGS, there is only a linear term. This will simply go linearly. I mean, let me draw it nicely. Okay, since I am not able to show it, let me explicitly write it. This is quadratic. Okay, and obviously in this region this transistor is in saturation, SAT, and beyond this region it's in linear region. Okay. So now consider my VDS2. What should happen? VDS2 2, 3. Let me just color code it nicely. 2, 3. So first until VTH what will happen? Same thing happens, correct? So therefore the current will be 0 all through till here. Now VDS is higher, VGS has just gone beyond VTH. The current will be greater or lesser than VDS1? The current will be, yes, okay. So you are basically saying that because it starts in saturation, the current will basically be the same till that quadratic region, right? Okay, interesting. So then, yeah, that seems logical. Now, so will there be a point where this curve will not be differentiable? So okay, what I have drawn, is it correct or wrong? Why? Exactly, because it has to proceed in the quadratic region even further and then it will switch to the linear region. So that's where, so this will go like this until what point? this is VDS2 plus VT, and then it continues in the linear region. Okay, this will be quadratic and linear.